All right, so here we're going ahead and continuing with the next lecture for Chapter 15, Applications of Aqueous Equilibria. So we talked a little bit about how strong acid, strong base titrations, they're going to result in an equivalence point with a pH of 7. And they talk a little bit here about how over time certain amounts are canceled out, and they do this stuff in millimolar, which is just a mole times 1,000. Just to try to keep the units a little more simple. That's really all they're working through here. They work through a number of steps before the equivalence point, where we can think about the system as being, dominated by the starting acid, and then the strong base decreases the amount that's present, but we don't really have a whole lot of built up in the other direction yet. And of course, since this is a strong acid, strong base, we're never really going to build a buffer, so it's always going to be based upon the current present amount of H3O plus that we can use to get the pH, until we kind of flip over and have canceled out enough of the acid that the solution becomes basic. We're not going to be able to use we're not going to really use the base quantity. We're just going to be decreasing the acid quantity. But this basic thought process is also going to be important when we look at the weak acid, weak base situation. So at the equivalence point, like I said, we'll have 7, and then past that point, it'll become basic. So this is pretty straightforward. Like, this is a simple curve, and the basic idea is just to use the concentration and to see how the concentration changes by addition of a certain amount of base. So we could convert whatever volume of base it is to the amount of moles added, subtract the moles from each other, get a new molar amount, put that back in the volume, and continue. That's really what the book is trying to show you how to do here. It's trying to show you that you have H3O plus, and then you've added some amount of OH minus, and you can subtract them as moles from each other, or in this case millimoles, and then put them back in the new total volume, because the volume is changing too during a titration. You're adding two volumes together, so you got to put them back into the new volume to get a new concentration, because it's only a concentration that you can plug in to calculate a pH. You can't use the amount in moles. You have to use the actual concentration in a given volume, and that makes a big difference. So that's the check that we're doing here. Okay, that's the idea that we're looking at. So they give us this really kind of overwhelming chart. Again, it's the important part of this is being able to see how up to the equivalence point the pH is still acidic up until it makes that change to become neutral, and then from then forward it becomes basic. And this change happens very quickly. It happens quickly as you approach the equivalence point, and then it moves away. Okay. This is where it gets more interesting, the weak acid, strong base titration. This is the typical titration that students would do in a CD course, typically in a 151 level, but we're going to dissect it down so we can think about it in terms of buffers and equilibrium constants and things like that. So if you've already done something like this, then you'll be a little ahead of the game. So before the equivalence point, we can use the Henderson-Hasselbalch equation and describe the system as a buffer dominated by the acid that started out in here as we're adding the strong base. We haven't canceled it all out yet, because as we add the strong base, we're generating an amount of the conjugate base, and that's what goes into the Henderson-Hasselbalch equation. So we can take the concentration of this added sodium hydroxide, make our volume conversions as necessary, and then plug them into the Henderson-Hasselbalch equation, get a ratio. We can, in this case, use mole numbers, millimolar numbers, which they do, because that ratio already accounts for the volume. So you're able to do that because both of those are present at the same time in a given volume. So in this stage, we can use the Henderson-Hasselbalch equation to help us calculate the pH, because what we're basically forming is a buffer up until we reach this point of equivalence, where now as we continue, our system is going to be dominated by the added OH minus. So let's continue here and think about what's going on. So halfway to the equivalence point, we will see that the pH will equal the pKa. This is the truth in titrations. This is an important concept. We'll pass through this buffer point, and that this is due to the Henderson-Hasselbalch equation. At the equivalence point, okay, all of the initial acid is now base. So now we're able to use the Cheesy equation with the basic salt, okay, and calculate what the pH is there. So this is pretty straightforward, okay. because at the equivalence point, all of the initial amount is gone. But we have to account for the new volume. We just have to fix the volume, okay? That's all we have to do. We just have to fix the volume. But all of the moles will be canceled out. So like, I just want to point this out to you going back here. So if we started out with some 0.1 molar acetic acid, all of that acetic acid is now acetate. But the volume might have changed around us, so we can convert this to moles using whatever the starting volume was, and then put those moles into a new volume, and then that we can then go forward. That's all we have to do. That's what they do down here. They convert that to moles, 4 millimolar, and then they put that in the new volume and get a new concentration. And with that concentration, that's a weak base. So we can use the weak acid, weak base, cheesy equation and calculate the pH at the equivalence point. At that point, it's relatively easy. After the equivalence point, okay, at this point we have this weak base present. Okay, it's all neutralized, and now we have more hydroxide present. So we will have to somehow account for that. The hydronium ion concentration and the pH can be calculated from the excess. From the principal reaction is negligible compared to the hydroxide ion added. So at this point, it would just be governed by the added hydroxide, unless it's just such a little amount that we could actually set up a real equilibrium for that. But generally, no. Generally, once we start going past this, the amount is so great that we can get the pH just from the added amount of sodium hydroxide. So that's what they put in here, the amount of hydroxide ion present. Let's see, the total volume is 90 mils, so we've still got that part. We have more than enough to cancel it all out, so we're able to just think about this as just all purely hydroxide, and just think about the hydroxide ion that's present, and that'll set the pH. So basically, we can think about these as like 3 different kinds of problems. These titrations could be thought about as 3 different kinds of problems. The first type of problem is in the initial rise stage, where we can use the Henderson-Hasselbalch equation. This part in the middle at the equivalence point, where we can calculate the pH by using the cheesy equation. And then past this point, where we're just using the pH of a strong base. And again, see, our indicator is close to our equivalence point, but it's going to miss it a little bit because it's not quite lined up. Sometimes it's hard to find something that lines up perfectly. But this is essentially what the titration curve looks like for the titration of a weak acid with a strong base. And this shows how the curvature changes. You get less and less curvature as your acid gets weaker and weaker and weaker, because there's less neutralization really happening. We saw that earlier with the Kn idea. So this now is the inverse. This is with a weak base with a strong acid. You see that the S is curved in the other direction, but the basic shape is still the same. You still have an equivalence point. These reactions work the same basic way. The initial stages before the equivalence point, we can do our calculations with the Henderson-Hasselbalch equation. Whether we do it in the frame of an acid or as a base, it doesn't matter. When we're before the equivalence point, we calculate this as a Henderson-Hasselbalch type stage, where we've added something, but not otherwise. Before the addition of anything, it's just a regular weak base equation, right? At the equivalence point, it's now a weak acid equation because everything has all been converted. And then beyond that, it's controlled by the acid addition. So similar situation to what we had before. So here we look at the protonation of alanine, okay, and we add hydroxide to this, okay, neutral form and then an anionic form. And they give us these different Kas for each of the process, right? They say here the dissociation equilibria, okay, so that's our neutral form, okay, acting as in, that's our protonated form, sorry, that's our protonated form, acting as an acid, okay, and then, but that's a pretty small Ka, and then our next one, our neutral form, has a smaller, has a higher pKa, so it's a weaker acid, right, by 7 orders of magnitude. So they talk here about diprotic strong acids, diprotic acid strong base, okay. So with these we see 2 curves in our setup. So before any addition, again, the principal reaction is just the presence of that first Ka1, and that'll typically give us the pH using the cheesy equation. We use Ka1. We showed how we could do that before. In this zone, we've got a buffer against the second, the deprotonated form in this case. And that's just the first equilibrium. And then halfway to that point, we'll get that this is pH is equal to the pKa. At the first equivalence point, we could again treat everything as though it's in that next form. Okay, and also we can get the pH at the first equivalence point by using the two Ka's together, and that will give us a sense of what's going on here. That actually is an easier way in these equivalent stages to do that, because we'll have presence, we'll have everything converted all the way over. They said that at this point, at the first equivalence point, the pH at this point equals the average of the two pKa values, because we're right in between the 2 points. So that actually kind of makes sense. So this ultimately yields a theory you might have heard in a biochem class, that the isoelectric point for an amino acid is its first pKa and then its second pKa divided by 2. Isoelectric points can be used to separate mixtures. So that's interesting if you have a diprotic system, but there are diprotic systems that are not necessarily amino acids. But it's interesting because this idea still works for all of those as well. This is what the shape of a curve looks like when you have multiprotic acids. So the first curve you can see is the strongest one, okay? And then the subsequent curves tend to be pretty weak. There are titrations that we can do in a lab situation where we titrate citric acid, which is like triprotic. And the third one is even worse. It's so shallow you really don't even see it. But you can see that this one, pH is equal to pKa. That's our buffer region. Then our equivalence point, isoelectric point. Then pH is equal to pKa2, another buffer region. And then another equivalence point up here. Halfway between the first and second, it's converted. So pH is equal to pKa2, okay? Then at the second equivalence point, we have a basic salt, and we can do the same basic idea once we're past that. The only real interesting thing was at this first equivalence point. That was interesting and new. But past that point, this behaves essentially like any other titration that we've seen in terms of its behavior and characteristics. So calculating the pH for the diprotic strong base titration, they give us these different volumes, and we have to figure out sort of where we're at in each of these situations. So what we would do is convert these to moles. They're titrating 30 mils of this solution of the protonated form of methionine with 0.09 moles of sodium hydroxide. How do I calculate this pH at the following volumes? So I would first want to convert these to moles or millimoles, depending on the preference. And then I could figure out that in the first scenario I have equal amounts of both, which means that I'm at the isoelectric point. It says here the added base is just enough to reach the first equivalence point, converting everything because they're the same number. What I end up with is the same, so they'll cancel each other out. And then I can get that by using this formula. There are a lot of quick ways to move through these, so we don't have to spend all our time in a lot of ice charts, or we want to minimize all the extra Henderson-Hasselbalch we don't need. So in this case, we've added this. The added base converts everything, and then convert the remaining HA to A minus. So that means that we're able to just use pKa2, and at this point we have a half situation, so our pH is equal to the pKa2, and that allows us to calculate the next pH. Then this amount sets it up so that we're in the Henderson-Hasselbalch, we're in the buffer region for pKa2, and we're able to set up a buffer with the leftover ratio amounts. So really what these problems are about is figuring out sort of which region you're in, what happens. So you're going to want to convert everything into moles so you can compare the relative mole amounts and figure out where you are on this sort of chart and what problem or equation might be most useful. Again, On an exam, I would not have a question this complicated. I might only have one, like A, B, or C. And you'll need to figure out where that puts you. And it might be that you have an easy situation like A if you know all the right equations. I'm really not into creating situations where you have to spend a lot of time with ice charts and additional complications in my problems on an exam. So I'm looking for things where you can use quick ways to get answers or to get ballpark answers so that you can move through. These tests can be intense, so I do want to try to keep down the load of making ice charts and doing complications. The real difficulty of problems like this is keeping track of the volumes that end up happening. Because if you make a mistake and put something into the incorrect volume, you'll get an incorrect concentration and you can have a lot of trouble. So that's my major recommendation here. So now we're finally to solubility equilibria for ionic compounds. So this is where you have something that hasn't dissolved, or something that doesn't dissolve very well. If you have something that dissolves really well, it has a really good solubility, then the equilibria, the KSP is a huge number. Like for table salt, okay, like sodium chloride dissolves really well in water, so you don't really have a solubility product constant that really is discussed. It's just a very large number. It's kind of like for a strong acid or a strong base. So typically when we're looking at solubility equilibria, we're looking at things that are not very soluble, what they might call insoluble or sparingly soluble. So the example of this is calcium fluoride, which is not very soluble. So we set up a KSP expression to describe that solubility, which is the product of these ions, and they're raised to their corresponding powers just like they would be in an EK expression. Keep in mind that this 2 is here. We're coming back to needing those things for these solubility equilibria, where we didn't need them so much for acid-base problems because we generally were only releasing one proton or reacting with one hydroxide at a time. So keep in mind that these exponents are going to be critical. So they say we set this up and we get a general formula for this. Again, it's the same as what we would see for an EK, but we leave out the pure solid. It's the same basic idea. So we want to be able to write expressions. That's important. That's the starting point. So when we see these systems, we can write a KSP expression, and you should be able to do that. Again, I'm just taking the ions. I've got to use it squared because there's a 2 in front of this, and then I got to put this in here. It's not the charge, it's the stoichiometric coefficient that we got to remember to put in here from our previous chapters. So how do we measure KSP and solubility? Well, there are a number of formulas that can associate the solubility with the KSP. KSP is not solubility. There are connections between KSP and solubility, but they're not necessarily per se direct. Just keep that in mind because of the squaring that we may need to account for. They say in this book we will calculate approximate solubilities assuming that ionic solutes are completely dissociated reaction 1. In the case of PbCl2, ignoring the second equilibrium gives the calculated solubility that is about too low by a factor of 2. Okay. So many of these salts do not dissolve very well, so they have KSPs that are very negative. They favor not being dissolved. That's kind of the general expectation. So you can see many orders of magnitude KSPs can range here from things that are a lot. Now remember, also KSPs, like all other Ks, are influenced by temperature. That's why generally when you heat something, you can increase its solubility. So some of these things with higher KSP values might be soluble if we raise the temperature. But generally we want them to become numbers bigger than 1 in order to really start calling them soluble. But solubility and KSP are distinct concepts, related but distinct concepts, so keep that in mind. So we're given these concentrations to start out with. This is where the common ion effect will be able to come in, right? Because if I have some insoluble or sparingly soluble material and I put it in something that already contains one of those ions, it's definitely not going to dissolve. And that's one of the things that we're going to see for sure here. So now we're able to calculate the KSP by plugging in these concentrations. Again, it's pretty straightforward because this is similar to any other K-type problem. Now calculating KSP from solubility, this is where it gets a little more complicated. So they tell me that it has a solubility, okay, so saturated solutions are prepared by dissolving solid as you chromate in water, and it has a chromate concentration of this. Calculate KSP. So we set up a KSP expression, and we can calculate the concentration of the other ion because we get 2 of those, 2 silvers, for every chromate. And we can see that in the equilibrium formula that we write out here. So since we know the concentration of the chromate, we'll need twice that to get the concentration of the silver. And then we can plug those two in and calculate the KSP. Solubilities are often described in terms of like the whole compound, or in terms of like one unit of the compound, like the chromate, or like this whole compound, which would need to be doubled for the silver. Sometimes the way a problem will put this is it'll give you just a solubility for this compound. What they're saying is to do this same thing. That solubility would need to be doubled for the silver and kept the same for the chromate. Sometimes they tell you that solubility is a particular ion like they do here, but keep in mind sometimes they don't. And when they don't, it still works the same way. So they want the solubility of magnesium fluoride here in these units, but I have to get the KSP from an appendix. Keep that in mind, that they went and got this solubility, the KSP, from an appendix. They didn't give it here. On an exam, I will give you all of those things. Please do not memorize those. To convert the solubility from units of this to grams, multiply by molar solubility by its molar mass. Okay, so we're able to get the molar solubility, which is generally what we want. Okay, so this is an A. We've summarized this expression. So this is X and this is 2X because there's two fluorines. That's just to make sure we get the 2 in there. So sometimes it'll be nice to make an ice chart like this just so we can remember that we need to put a 2 in front of that fluorine. So then we can work this out. And if we know the KSP, this X is the solubility. So the solubility will be the concentration of whatever something is to the first pair. If this was a 2 here as well, if there was a 2 here, then that would also get a 2. And X would still work the same way. If this was a 3 in front of the magnesium, there'd be a 3 in here, and this would have to be cubed, and it would work the same way. Just keep that in mind. This X is our molar solubility. So we work out the molar solubility. It's basically our change in a certain way. Like it's our change number. If we built this out as a full ice chart, it would be our change number, assuming that none of these ions are present currently. So then we just have to convert this molar into grams per liter using the molar mass, and we're good to go. So that is the end of this particular lecture part of Chapter 15, and I hope to see you all in the next one. Thank you.